Hello. How are you? Hello, Dr. Vladimir. How are you?
Hello,
Do you hear me?
Professor. All good, all good. Thank you. How are you?
Thank you so much. Thank you so much.
Glad to see you.
Glad to see you too. Thank you. Before I forget, I'm going to send you the email addresses of these two guys that I contacted and got the approval after the meeting.
Excellent, and thank you in advance. What can I say?
Thank you.
Thanks.
Thank you.
Thank you.
Good afternoon, my dear colleagues. Welcome.
Afternoon. Afternoon. Afternoon.
Good afternoon.
Okay.
Hi, good
Hi,
afternoon.
Deta.
Good afternoon.
Miss Fatma, good afternoon. Dr. Abdul Hadi, good afternoon. Thank you so much for attending. I'm just waiting for a couple of more minutes and then we will start.
Hello, Professor.
Hello, Dr. Yaman. Welcome.
How are you? All good. Hello, everyone. Excuse me, I'm just fixing my USB, so there seems to be a problem with my speakers.
Okay. Good afternoon, everybody. Thank you so much for attending for today's session.
Thank you.
Today, we are going to talk about, again, this is a second session for regression, actually. We will continue about talking regression analysis. What we are going to talk is I'm going to give you the other regression models as an example, where you can use them in which, let's say, circumstances, in which cases you will need to use the other regression models. And I'm not going to go in detail for them, but I want to give you a good list of models. There are a couple of more ones that I will not be able to cover here today, but I will also mention those by name. And I will also talk about a little bit more in detail regarding moderation and mediation in regression, in linear regression. And we will do, hopefully, when we have time at the end of this session, I will do a couple of more regression analysis using SPSS. And I will also try to show you how to draw the moderation effects and mediation, how to understand using the analysis through SPSS, because both of them requires a couple of steps in interpreting the results. So this is the main subject of our today's session. So let me start by sharing my screen with you, my PowerPoint, and then can you please confirm that you see the screen, PowerPoint?
Yes, we can see.
Thank you so much. Thank you. So, the types of regression. I'm going to start with the different types of regression. You know, the last session, we talked about mainly simple linear regression and the multiple regression. Both are very pure linear regression models.
If you
In
can zoom out a
general-
little bit, Professor, because it's cutting in the slides, the PowerPoint. You can zoom it out a little bit.
Now, is it okay?
No, I don't know. At least from my side, it's not.
Same here.
Yeah, we can see half the slide only.
Now I put it in the show mode.
No, it's not. We can see half the
Okay,
slide only.
I will stop sharing.
And reshare again, absolutely.
Yes, yes, I'm gonna do it like that.
Maybe we do full screen also.
What about now?
Yeah, now we can see
It's
it.
good. It's good.
Okay, okay, good. Thanks for the heads up, by the way.
Anytime.
In general, regression is a predictive modeling technique, actually. Again, as I mentioned in the previous session, it's one of the main techniques in use in machine learning, also in data science. So it evaluates the relationship between the dependent and the independent variables, and also the strength of the relationship it analyzes. So it can be used for forecasting, it can be used for time series modeling, and at the end of the day, there are two main goals. First, again, to predict the dependent variable, and also explain the impact of changes in the independent variable based on the changes in the dependent variable. So it means at the end of the, as a conclusion, we say that if we explain it as this equation, we will understand that if one unit changed in the x variable, how much it's going to create a change in the dependent variable. If our example would be, let's say, students, if we say the x is the time or amount of time that student studies, and the y is the exam score, we can say that we can find out that, okay, if you study 1 more hour, how much your exam score will change. So I can predict this. Or if in total you work 10 hours, how much your exam score might be as a prediction based on the analysis. So regression, again, is mainly a prediction methodology. So based on the nature of the variables and based on the nature of the relationships among variables, okay, there are different types of regression models. However, each regression model, of course, has its own assumptions to meet. Today, we are going to talk these different regression models, and you're going to need which one of them in which circumstances again. But I would like to mention one important thing here before going further. And I'm also telling these things in all research methodology sessions in any level. Actually, your data is the essential ingredient. I mean, the sampling and the data is most important ingredients in all actually statistical techniques. And of course, in regression models. Because no matter how advanced methodology you use, how advanced techniques you use, how advanced software you use, if your data is not good, if your data is not reliable, up to date, so at the end of the day, the results, the interpretation might go wrong. So that's why it's always the data, you have to have the reliable data in your hand, and you have to understand the data, and then you use this kind of technique. So just in parentheses, I wanted to emphasize this issue once more. So we will start with simple linear regression again. This is the most basic form of the regression models. Model consists only one dependent variable y and only one independent variable, which is x. So both dependent and independent variables are continuous variables, by the way. This is one of the important features in this simple regression. And it means that they're measured as an interval or a ratio. So they can take any numerical value. And the relationship between them, of course, we assume they have a linear relationship. So it's again, the most basic form of all the regression models. And when we are doing the mathematics behind this regression, as you would remember, model calculates the best fit straight line by minimizing the total squared error. So the model tries to fit this, as you can see in the screen, red line as a straight linear line, and try to find out the best slope for this line to have the minimize the total squared error of the data. So this is the simple linear regression. And then we talked about multiple linear regression. The only difference is in multiple linear regression, we have more than one independent variable, right? Now we have x1, x2, x3, and up to xn, whatever you use. Because they have more than one independent variables, now we need to meet some assumptions in this multiple linear regression. For example, one of the important issues was multicollinearity. Because based on the multicollinearity, we assume that different x's, I mean different independent variables, actually measured independently from each other. So we assume they are not correlated. However, of course, by nature of the social science, they have some correlation between. So by using, remember that we check VIF, variation inflation factors, we check condition indexes, just to evaluate these multicollinearity between. Another one you would remember, heteroscedasticity and normality of errors, which we also need to need to check and need to confirm they're not affecting our linear regression model. Again, these features actually comes to the fact that we have more than one independent variables in the multiple linear regression. So again, this model also calculates the best fit straight line by minimizing the total squared error. However, in this multiple regression, based on the number of independent variables, of course. Now, rather than best line, it's going to be like best fit surface. Again, minimizing the total squared error of all the independent variables in the equation. So this is the two basic regression analysis, regression equations that we already discussed in detail in our last session. So what are the other types of regression models? The first one I would like to mention is the logistic regression, or in some sources they call it binary logistic regression. When do we use logistic regression? We use it when the dependent variable is discrete. When the dependent variable, I mean the y variable, the resulting one, is just like true, false, pass, fail, 0, 1. It can only have binary value. Then we can use this logistic regression. So in logistic regression, actually the coefficients of the independent variables are calculating the probability of y occurrence of the y variable. So we use logistic regression. Again, independent variables are used to predict the probability, not to predict the variance in y, like in simple regression and multiple regression. Now in logistic regression, again, the coefficients are used to predict the probability of occurrence in the dependent variable, not the unit change. Okay? So for this purpose, our regression formula is not like linear formula now. We call the methodology or approach that we call logit function. So based on the logic function, now x and the coefficient and the slope and the coefficient of the x are calculating the logistic odds of the y variable. So when we apply this in SPSS, for example, and when we have the coefficients, the important part is how are we going to interpret? Actually, to interpret the results, the best way is to take the exponential of the coefficients, and then we will get the odds ratio for each x variable. So what does it mean, the odds ratio and the exponential coefficient? So let me give you an example. Let's say that we have a logistic regression model, and we have coefficient like B1, B2, B3, something like this. And let's say that for one example, we have x1 and its coefficient is b1. So it means that we are going to take the exponential of the coefficient b1, okay, and the result is going to give us the effect in odds of the y variable. If this exponential, after we take the exponential of the coefficient, if we have the result 1.34, for example, it means that the 1 unit change in x will result in 34% increase in the probability of the occurrence of y. Just be careful about here. It doesn't mean that 1 unit change in the x will result in 1.34 point or unit change in y. It actually 1 unit change in x will result in 34%, because 1.34 means it was 1 before, and by the change in x, now it's going to be 1.34. So increases 34% in the probability of the occurrence of y. So in logistic regression, where we can use it? Again, we can use it in manufacturing sector if it is, for example, when you produce something, if your product is working or broken, or in hospitals, if a person is has the illness or not, is sick or not, or a pass or fail, or 0 or 1, or or these kind of things. So if your dependent variable, if your y variable has a binary nature, then what you have to apply is a logistic regression. That's why logistic regression doesn't have a linear distribution, of course, linear line. It has a line, what we call sigmoid line. Okay, it's like a S curve because, as you said, based on the R studied here in this example, test passed or not. This student passed or not. So it has only 0 value or 1. And this line shows us, for example, if we want to interpret on the curve, we can say that if the student worked 4 hours, if you go up to 4 hours, if you go lane, it has a 75% chance to pass the test. This is how we interpret the results of this regression. If he works 2 hours, it only has maybe 15% chance to pass the test. So this is how we use the logistic regression and how we interpret the results of the logistic regression. Of course, I mean, I don't have enough time to go in deep of the mathematics, but if you want to use it or if you need to use it further, I can provide you the resources to how to apply it, how to in mathematical and in SPSS. I will, of course, show you today how you can apply logistic regression. So this is another version of the regression. One version is, we call it polynomial regression. Polynomial regression, as you can understand from the regression equation here, now we are not talking about the linear relationship, we are talking about a non-linear relationship or quadratical relationship. So this technique of polynomial regression analysis is used to represent a non-linear relationship between dependent and independent variables. It's a variant of the linear regression, of course, but the best fit line is not a straight line anymore, it's a curve instead of this. So if your data is distributed or scattered, something like this, instead of trying to fit a straight line, maybe a curved line might be a much better fit and might give you a much better explanation on the context that you're looking for an answer. And this polynomial regression actually is also used to understand the differentiating effects of the differences between two dyadic variables on the dependent variable. Let's say in this graph on the right side, so there are two X variables here, supplier dependence, buyer dependence. And based on its value, we are trying to understand what will be the buyer satisfaction. So we want to understand, okay, these two X variables are dependent each other, are kind of dyadic for each buyer. We have a supplier dependence and buyer dependence, and based on their values, we will try to understand the buyer satisfaction. So this is a curvilinear relationship again, instead of a straight line. So sometimes, if you have really, when you do your analysis, I strongly recommend you, if you have not significant results, you might go and see visually how your data is scattered, and then you might want to try to apply this curvilinear relationship to see if there is any significant relationship between your independent and dependent variables. Another regression model is what we call ridge regression. Ridge regression is a very specific type of regression. We need to use it when the data or components, factors in your model really shows a high-level multicollinearity. So if you cannot get rid of this collinearity, and the ridge regression technique is applied, for what? Actually, to mathematically reduce the effect of multicollinearity. Okay? While I'm saying this, while least squares estimates that we are trying to apply in a regression, it's supposed to be unbiased in multicollinearity, but if there is a relationship between two x's, their effect on y, their influence on the dependent variable might change, might diverge from the actual value. So this is why the ridge regression comes into play. And again, what it does, actually, in the regression model, mathematically, it applies a kind of penalty value. The penalty value is used to reduce the errors by biasing the regression estimates. So this is what ridge regression does. And the lambda variable here, as you see in the equation, is actually used to resolve the multicollinearity problem by reducing this inflated, let's say, effect coming because of the correlation between the two or more independent variables. And there is a lasso regression, very similar to ridge regression. Again, the lasso is an abbreviation, and it stands for least absolute shrinkage and selection operator technique. This technique is also used to penalize this inflated magnitude of the regression coefficient. This inflation is, I mean, we assume that it's coming from this multicollinearity issue, and it unfortunately causes the wrong interpretation of the results. So the difference of lasso regression of the other one, in lasso regression, you have the chance to choose the variables. The other one, you don't. So again, I'm not going into mathematical detail of this. If you need to use them, I can provide other resources to do this. And there is Bayesian regression model. Bayesian linear regression, actually, this is a linear regression. However, this technique uses Bayes' theorem to calculate the regression coefficient values. What Bayes' theorem says, maybe you would remember from the probability, let's say, theories. In the Bayesian approach, the data are supplemented with additional information in the form of a prior probability distribution. So it means that we already know the prior conditions, prior distribution. So in this technique, we are not trying to find the least squares, we are trying to determine the features posterior distribution. So as a result, the approach gives us stronger, actually, result compared to the linear regression, because in simple linear regression, we compute point estimates of our parameters and use this estimate. But Bayesian linear regression, we estimate distribution over the parameters and prediction. So first, we have the distribution. We already know the distribution according to the Bayes theorem, and we are trying to find out the result that fits that distribution. So that's why, because we know the distribution, now we are a little bit more sensitive to the noise created in the regression, and we might have much, let's say, robust results compared to the linear regression models. It's a technique that recently becoming common, and now I'm seeing in the scientific articles they are trying to, let's say, employ this Bayesian regression and more compared to the ones in the literature, let's say. There is quantile regression. Quantile regression is again a subset of linear regression. In econometrics, you might see it a lot, by the way. And when the linear regression requirements are not met exactly, especially when we have some outliers in the data, then quantile regression might be a solution. Quantile regression, we use it to estimate a specific quantile or a percentile of a response variable. Let's say that if you want to predict the expected 90th percentile of exam score, then this quantile regression might be a good solution for you. Again, the purpose is not gives you the direct estimates, is it give you the some percentiles of the dependent variable. I mean, according to my own experience, it's one of the regression models that you really see very rare. Again, it's mainly used in econometrics, because in econometrics, I'm not an economist, I'm not a finance expert, but maybe our dear colleagues can also give additional information on this one. In econometrics, it's very, very common to have outliers, because we are having the data regarding to all these differentiations based on the currencies, based on the money values and everything. So it's very common we have outlier values. So that's why it's one of the technique used very commonly in econometrics again. There is Poisson regression. Poisson regression actually is used if you have a count data. If our y variable, if our dependent variable is something that we count over a certain amount of time, area, or another consistent length of observation, we use this technique actually. So in Poisson regression, the model gives us the changes in the independent variable is how much associated with the change in the counts of the in the dependent variable. It's a little bit similar to logistics models, because logistic model at the end of the day, 0, 1 is something that counts, but the main difference, of course, it's only receives 0 and 1. In Poisson, we have counted numbers for some time. Let's say that we might use Poisson regression to estimate or predict the number of calls that a call center receives daily. Poisson models can also be suitable for the rate data, for the proportions. So as you know, the proportions is calculated as a count of events divided by the units exposure. So for this proportions, for this rate data, Poisson models also a solution to estimate, again, the variance or to predict our dependent variable. And one of the most important one, actually, multi-level regression is not a different kind of regression. Actually, it's an approach that should be considered when you are calculating linear regression. This is actually, I want to mention about this multi-level regression. In reality, in practice, multi-level regression actually is needed in most of your studies. And because it's a linear regression when the level of variables are different than each other. What do I mean? Some variables are measured in individual level, for example. Some are in organizational level, and some are on even industrial level, as in this nested structure. We call it a nested structure. For example, we have students, but students are in classrooms, classes are in schools, schools are in the area, and the area might be in the country. You can even go further up. How this affect? I mean, I'm gonna give you an example, okay? Let's say that we have two different classes, and we have 2 different instructors, and both are teaching mathematics. Okay, so when they have a test, okay, it's not only the how much the student studies, also there is an effect of the instructor, right, on the study. So if you try to build a regression model and try to connect the amount of time they study and the exam score, and if you don't reflect the effect of instructor, you're going to end up a wrong interpretation, because the exam score is not just related or dependent on the hours, it's also dependent on the quality of the instructor. So in multi-level regression helps us, okay, to reflect the effect of this group effect on the lower level. So it helps us, in this example, it helps us to reflect the effect of the instructor on the student's success. For example, it's in real life, we always do that, right? When we try to find a school for our kids, right? If the success is only depend on the time they study, why are we trying to find a quality school? Because there is also an effect of the school on our kids. So, but when we are building these regression models, somehow we need to show the effect of this group. So multi-level regression is the way to do it. So it provides a much better inference from grouped data. Okay. So multi-level considers the influence of the group on the individual, and it explains how much of the variance in the dependent variable comes from the individual and how much of it comes from the group. So when a student got the mathematics final exam at the end, now we will know how much of this score coming from the student himself or herself, and how much of its success coming from the instructor. So as a graph, for example, let's say that we have this data and we have 2 groups. Continuing going again from the same example, let's say that this middle value is the average of the all sections, okay? And there is this section that is shown in orange ellipse, and the other is blue. And when we have a different average of the sections, you will understand that there is an effect of the instructor on the section, right? So, but in the regression, if you don't reflect this effect, then you might end up, because there is, if you try to find out this difference from the main average of this student, actually this student is different from that section's average, and that section average is different from the main average. So we have to find out, we have to calculate this both difference, is this both variance. So, and how much of this variance coming from the student himself or herself, or how much of this variance coming from the group itself. So this group effect should be included in the model. So we somehow have a mixed model for multi-level regression. The first equation gives us the within group differentiations. Second is going to give us between group differentiations. And the final model will end up considering, again, differentiation of the individual and differentiation of the group. Actually, again, as a real example, I wanted to share with you, this is an example from an article that I was a part of the team, and we had the chance to publish it in very recently. It's a 2023 publication, Journal of Business Research, with my colleagues, the professors from Turkey and USA. And we had this analysis, for example. So as you see, there are some variables in this model are measured individually. So for example, this is individual performance, this is individual innovative performance and extra role performance. However, on the team level, there is team cohesion, there is leadership. So now we know that the leadership has an effect on the employee's performance. However, if we have different groups, okay, if you have different groups, the individual's performance is dependent on their own individual characteristics, but however, it's also dependent on the leader, but the same leader affecting the group members in the same way. So how am I going to differentiate how different leaders give different influence? This is the way that you can build your regression model. So you have to show the individual and the upper level variables, and then you have to do your calculations based on this modeling technique. So multi-level regression, SPSS, do it, but a very, very long way. So there are other softwares that you can use if you want to apply multi-level regression, like HLM, like M+, like R. You can apply multi-level regression in using those softwares. And as a final part of our presentation today, I would like to talk about moderation and mediation. Moderation and mediation is an approach again in the linear regression. As you can see in normal simple regression, we have dependent variable and we have independent variable or independent variables. And we are trying to analyze and predict the dependent variable based on the variations in independent variable. And we have two more concepts on this. We have mediator and we have moderator variable. So what are these actually? So moderation and mediation is a form of regression that allows us to analyze how a third variable affects these relationships. So, and in regression, some of them might be moderate and some of them might be linking variables. Now I'm going to start with the moderation. So what moderation means in theory or as a meaning, and I'm going to give you also how we should interpret it, how we understand it. Let's say in this simple regression, we have an X variable and we have a Y variable, okay? And let's say for the whole sample, if we don't make any grouping, if we don't make any kind of categories, the whole sample, the level of relationship is 0.5. The coefficient is 0.5. Okay? However, as in my previous example, if the student has a good tutor, this study, the time of study or amount of study might have a stronger result in the exam score. And students with a bad tutor or without a good tutor, let's say, they might end up lower. So if we have two groups in this example that moderates means, as you see from here, there is a third variable. This third variable affects the nature of the relationships. Okay? So again, having a good tutor, if we consider it as a variable, it makes it stronger. Having a good tutor is low, then the relationship is changing. Now it's much weaker. So there is a third variable. Usually these third variables are control variables, right? Like culture in the organization, like culture in the country, like I don't know, some age, for example, gender, for example, education level, for example. These things might be a control variable, might be a third variable that might change the nature of the relationship. Okay? So again, how we show it as where we call moderation, we have an X, we have a Y, and we have a Z variable that moderates the relationship. So this variable affects the relationship itself. Okay? So how are we going to know by equation? So we are going to use multiple regression that we use, and we simply include X and Z variable as a predictor. I put it wrong, I'm changing it at the same time, as the predictors of Y. This X variable is X variable, Z variable is the moderator. And we create a variable X times Z. It's actually, we multiply 2 and create a third variable, okay, in SPSS. This is as simple as it is. So we have X variable, we have moderator variable, and we will create a third variable. We will compute the third variable by multiplying X variable and the moderator. So when we will understand if the moderation is significant, so if this multiplied XZ variable is significant, then we can say that yes, there is a significant moderation. Okay. This is the way that we understand. Okay, when we do it, the question is, okay, how it's going to affect the relationship. So then the second thing when you do the analysis is to show the effect in terms of slope. So in terms of graphs is the better option, of course. So now we understand that the level of or amount of studying, of course, has a positive relationship with the exam score. So as you see, if you study, if your value is high, your exam score will be high. However, if there's a good tutoring, this effect, the slope is much sharp, the effect is much stronger. If there is a no tutoring or there is a no good tutoring, then your amount of studying affect the exam score, but very, very low level compared to the other one. And SPSS luckily gives the code how you can draw this by using SPSS known as, or there are also a couple of good websites. They provide Excel sheets actually. When you enter the coefficients of the variables, Excel directly draws this relationship and gives you the result. So again, the moderator is a third control variable that changes the nature of the relationship between X and Y. Sometimes some moderator variables even make it from positive to negative, so based on the effect, based on the context. This is what we call moderation. Okay, what is mediation? Okay. So mediation is, again, I'm going to go through the same example, but I'm going to use it in a mediation. So in mediation, again, we have this simple relationship. Mediation exists if this doesn't happen like this, but if this effect actually going through another variable. In moderation, the third variable was affecting the relationship. But in mediation, the difference is now we find out the X is not affecting Y directly. Actually, is X affecting M and M affecting Y. Okay. So the amount of studying, we assume that it is affecting exam score. However, through the analysis, we find out the hours of studying actually affects our knowledge. And when our knowledge is high, we have a high exam score. So in this manner, we call these variables mediators or mediation analysis. So how are we going to understand this mediation exists or not using regression equation? So in this model, we have two effects of X on Y. One is direct effect. As you see, X has a direct effect on Y. However, X also has an indirect effect on Y through M. Okay? So we calculated A times B. So A is effect of X on M, B effects of M on Y. So total effect actually is the total of direct and indirect effect as in a mathematical manner. So how are we going to understand this? Okay. First, we need to understand if X really predicts Y without considering mediator. Okay, we need to check if there is a relationship at the beginning, and then we need to check if X really predicts M, and then we need to check if X still predicts Y when M is in the model. Okay. So this is how we understand this one. So first, we need to check if this is there without M. And then second, we need to understand if X really affecting M. And then third one, when we put M in this equation, what happens to this one? Okay? If still there or not there. So at the end of this, we have actually three results. One is M completely or fully mediates the relationship. When M is in the model, X no longer predicts Y. So I'm going back. If we put this one, if this relationship is going away, then we say that it's fully mediated. Okay. There is a second version, what we call partial mediation. Okay. Partial mediation happens, let's say, if M is in the model, this one doesn't go insignificant. However, its effect now is much less. So when M is in the model, if direct effect is reduced, but still significant, that we call it partial mediation. Okay? However, if X does not predict M, I mean, if this is not there, or if this is not there, or if this is not there, it means that there is no mediation between those three variables. So this is how the moderation and mediation exists in this linear regression. Actually, in social sciences, we use a lot of these moderation and mediations. It's very rare that you see the very simple X and Y relationship. I'm going to go back to this real article example. As you see here, this is what we call moderated mediation. As you see, there is a moderation here. It means that authoritarian leadership affects team cohesion, yes. However, differentiation of this leadership somehow affects the nature of this relationship. So this is what is called moderation, as I just explained. So the role of team cohesion is actually mediation here. How? Because we said that, yes, authoritarian leadership affects team performance, but not directly affects it through team cohesion. So authoritarian leadership affects team cohesion actually affects team innovative performance at the end of the day. Actually, this relationship is a negative relationship, by the way, for this research. And so this is again.
You can hear it.
Sorry, yes.
شوف
Yes, I
هذا
hear you now.
قاعد يتكلم
Is there any question? Sorry, I missed probably. Okay. I'm receiving some notes. Probably you have classes now in 5-6 minutes. Do you have any questions, my dear colleagues?
Thank you.
Actually, I'm eager to looking for some application into this because they are really interesting and helpful. They are refreshing at the same time. So I was hoping that maybe in the future, if it's not too much to ask, we could have another session. Maybe we could have examples like how to apply them in SPSS and other softwares that you mentioned to us. Like that would be very much appreciated.
Definitely, Dr. Yaman. Thank you so much for this kind reminder. We are really planning to conduct an applied session completely on how to apply the menus, the data, and everything. And my intention is to definitely to apply mediation, moderation as examples. And also, I want to show you how to conduct the logistic regression and the others through SPSS, because one of the main ideas here is also to show you how to use SPSS for these purposes. But because of the timing, unfortunately, but we are going to definitely deliver it. Thank you so much.
Thank you very much. Thank you, Professor. Very much appreciated.
Thank you.
Thank you very much.
Thank you very much. I actually saw one application when you were having the pulmonary regression about the optimal taxation, because sometimes you see that for companies, if it's around, I think 18%, if it's more than 80%, actually taxation goes down, the Ocon law, and it would be perfect to use for something like that.
Yeah, it's a good example, by the way. It's a good example because most of the time in real examples, they tend to use this categorical binary results, actually. I mean, for example, is the frauds, right? If this person is a fraud or not, this person is going to pay his credit back or not. So these kind of decisions are actually binary decisions, and the logistic regression is a very good way to find the probability. Thank you. Thank you for the example. Okay, my dear colleagues, for today, that's the end of our session. As you all know, this is also recorded and is going to be shared with you through our COB Secretary, Ms. Maha, or Dr. Vladimir. And we will have one more session this week. In this session, our idea is to give you ideas about the structural equations modeling. And I will try to show you through it using Amos. And again, at this time, I will try to apply the knowledge also using the software because it's a little bit different. So thank you so much for your attendance. Thanks a lot, and I wish you all have a great day. And
Thank you very much.
hope to see you in our next session. Thank you so much.
Thank you, Professor.
Thank you, Professor
Thank you
Albert.
very much.
Thank you so much.
Thank you, Professor.
Thank you so much, Dr. Abdadi. Thank you.